Hello friends, I'm 2563 again. In the previous video, we solved it using binary search, and in the current video, we're going to solve it using two-pointer sliding window method. Here, I'm not going to restate the problem statement. So let's look at the idea and quickly walk through. First, you don't need to specifically consider the indices. The reason is that as long as two elements in A or the nums list is such that A plus B is in the bound lower and upper, so they form a valid pair. The reason is that their indices must be different. Therefore, they must be one is larger than the other, right? But addition is commutative, right? That's a key point. So because of this, you can do sort for the original array and then find the count of valid pairs ending at each element. So in other words, you just need to focus on the elements. So this is the first point. The second point is that for latter element B, so we want to find the former elements A that can form valid pair with this B. So we should have this condition. So then actually we can do some transformation. So minus B in the three expressions here. So the principal A should be in this bound, lower minus B and upper minus B. B is the current element, right? So therefore, we just need to use to find all A's before B such that this star holds, right? So this can be easily done using binary search, or you can use two-pointer sliding window method. So here we are going to do two-pointer sliding window method as we stated at the very beginning, right? So the walkthroughs are still identical, right? So after you sort, you get a lower bound and the upper bound. Then you, for each element, 1, 4, 5, 7, you want to get the contribution. In other words, at each for the previous elements can form valid pair with the current B. So the thing is, how do we compute those contributions, right? So here, using binary search is a one way, right? Because for this way, for each element, we find the corresponding number of A's, but also we can use set decomposition in a big picture, right, in the whole way. So the thing is that we can find the number of A's satisfy this condition, and then find number of A's satisfy this condition, and then overall we do the difference. So with that said, let's look at the current way of doing this. First, I'm going to sort this one, right? Nums sort this A. And also, I'm going to introduce this length. This is just for convenience. And next, we do two-pointer sliding window, right? So L and R to be 0 and N minus 1. So first, we are going to count so within the upper bound. So this will be very straightforward. So L less than R, right? Then we check the condition. If nums L plus nums R is less than or equal to upper, right? So here, because this is less than or equal, and well, this one is strictly less. So we want to find the elements that can form valid pairs. So here it means that let me write nums L and nums R form a valid pair. So similarly, you can see we can start from L plus 1 and then nums L and nums R. All those are valid pairs because in between those L plus 1s are less than or equal to nums R. As long as the end is less than or equal to upper, so all those should be less than or equal to upper because the nums is sorted. So then we do some counting. So count within upper. It would be the end index R minus L plus 1, then plus 1. So this is the how to compute the two-side inclusive range, right? End minus beginning plus 1. So the algebraic result will be R minus L, but I will keep this format because it's easy to interpret. So if this case, we compute all the valid pairs starting at nums L. Then next we just increment this L. Otherwise, because it's too large, so we are going to decrement r by 1. So that's one part. So next we want to compute the count within lower. So again, run it. 0 and minus 1. So count within lower. So we can actually copy this loop and make some modifications. So first is this. So here I should write strictly less than lower, right? This is due to the set decomposition. And then count will be the same, right? Because and then this also be the same. So finally, we just need to return the difference of these two. So count within upper minus count within lower. Let me first test it. It's not right. Let me see where's the problem. So here LR and yeah, left R is less than or equal to upper. So we have this one. And here, let's see, LR. So yeah, I guess here we should increment. This is increment. So also here we should change this to be lower, right? So sometimes it happens if you copy things, right? You didn't do all the necessary changes. So here is increment, right? So here also should be increment. So now let's test it. Yeah, it passes the two test cases. Now let's look at the generic case. Yeah, it passes all the cases. So first comment I want to make is this, right? So here I write this essentially twice, but due to the less than or equal and the less, strictly less. So this is an important detail, right? So though you can wrap this each of the two into a function, but you need to pay attention to the less than or equal to and strictly less. This is the one comment. Another comment is a term complexity analysis. So you can compare the here with the previous one, previous using binary search. Here the term complexity analysis will be the following. So you do the sort, it's going to be O n logarithm n, right? And then you do the two sliding windows. Each is O of n, right? So basically you have O n. So overall, I guess, so the common part of this term complexity with the previous video for binary search is this sorting. And actually for the way to compute the contributions, so here the sliding window method will be overall a little bit economical or efficient. So but overall the full term complexity of the solutions in the previous video and in the current video are both O n logarithm n. So with that said, this is the second comment. The third comment is that in our channel we have playlists corresponding to both binary search and two-point sliding window method. You are welcome to do some practices using those two playlists. With that said, thank you for watching.